All right. Hi, everyone. So, welcome to discussion 2. I'm going to go ahead and share my screen in just a second. Just a second. And okay. So, I'm going to go ahead and have a slideshow from the beginning. So, I want to welcome everyone to our second discussion. You guys may not be here today, and that's okay. It's going to be recorded, so you can all watch it later. For those of you who are here, what you can do from this discussion for any reason, or you can not come to discussion for a reason, but for any of you who are here, if you ever have a question while I'm talking or whatever, you can either put it in the chat, or if you want to speak, of course, you can just like interrupt me to ask a question. I'm perfectly okay with that. But I'm not sure if anyone's here today. That's all right. So we'll go ahead and get started. Today's discussion will be about algorithm analysis and debugging. Okay. So let's dive in. So objectives for today. So the first thing we're talking about is time complexity. Then we're going to do a space and time complexity difference. We're going to talk about the difference between the two because there is a difference. Yeah, we'll see what it is. And then we'll talk about, we'll have a little review of that, right? And then we'll go over setup of VS Code debugger. We'll have an example, and then catch 2 installation. And we're going to cover some testing next week. Okay. So let's go on. So the first thing is time complexity. So time complexity, as many of you may know, I think we covered in program 1 and program 2. It is a way of like quantifying the amount of time an algorithm will take. So it's not at like exactly the amount of time the algorithm takes, but like it's able to identify like what kind of class the algorithm would fit, like how much time it would take, and it kind of identifies it based on like assuming infinite number or infinitely sizing, like it or n, like some arbitrary. So it's, yeah, we'll talk about that. But so it basically identifies how long the function is going to take as a function of like how big the input is, because the input may be any size. So that's kind of nice. So there are 3 different ways we can classify the growth rate of the function, or like of the or to use time complexity, right? So we have big O notation. Hi. Someone joined. So yeah, right now I'm going over the discussion slides. So yeah, as I was saying, so as for, oh yeah, and one thing for anyone here now, if you ever have a question about anything I'm saying, you can like interrupt me anytime, and yeah, or just put something in the chat, whatever. So far we haven't really covered anything. We just kind of read the objectives for today. But yeah, so the first thing we're talking about is time complexity. So with time complexity, yeah, it's a way of seeing how long an algorithm is going to take as a function of length of the input. So we can use 3 different methods of growth. So there's big O notation, big omega notation, and big theta. It's also small, but like we don't really use this. So big O notation is probably the one you'll see most commonly. It denotes the asymptotic upper bound. And then there's big omega notation, which is asymptotic lower bound, and big theta notation, which is a tight bound on it. So for example, if I have a function that's big O of like n squared, I mean, that could still technically be big theta of 1, because like it's an upper bound, so it's not a tight upper bound. So it could be anything larger. And with big omega, it could be anything smaller. So if it's like actually ON, it could still be big omega of 1. But usually what we do is we kind of use all 3 kind of the same, because we basically use like big theta for everything. We just call it big O usually, because it gives us well, it's kind of nice to use. Yeah, so yeah, we usually use big O notation, and we usually just say what the type bound is. So for example, for g of n here, if it's 5n squared plus 4n plus 2, that's the same as saying like big O of 5 times n squared plus 4 times n plus 2. But that's equal to big O of n squared because we dropped the lower order term. which we'll talk about. So then there's best, average, and worst case time complexity. So best case, average case, and worst case, they estimate the execution time based on the asymptotic time complexity. So the time complexity we're talking about here. So it's almost like you're assuming that the input size n goes to infinity, like because it's arbitrary. We don't know how big it is, and that's why we drop the that's why we drop the constants in front, because at infinity, 5 infinity is equal to infinity. So yeah, the best, average, and worst case are completely independent of the input size. And yeah, the differences depend on, differences of the input. So like example is bubble sort. So we think about bubble sort, right? If it's already sorted, then bubble sort just makes one pass, right? And in that one pass, it just doesn't have to swap anything. So we're done. Because bubble sort is when we have, like if we had 1, 2, 3, right? Then bubble sort's going to compare 1 to 2. It's not going to swap. It's going to compare 2 to 3. Not going to swap. So there are going to be no swaps, right? So as a result, that's our best case. But the worst case is when the input is reversely sorted, right? Because we have to do like 3, 2, 1. We want to sort to 1 to 3. It'll swap here and then swap here, and then we have to make another pass, right? Because then we have like 2, 1, 3, and then we have to move the 2. So we have to do 1, 2, 3. So that's our best and worst and average cases, is like what usually happens based on the input. But it either way, our time complexity remains the same. So like it's still big O of n squared because we don't know what the input is. So if we look at time complexities, this is the amount of time it's going to take. And we notice like as the input size grows really, really quickly, it becomes like untenable to use algorithms that require like O of n factorial or even O to the n or O of n squared. So we usually prefer algorithms that scale a little more nicely, like big O of n, big O log n, big O 1, big O of n log n, because they run a lot faster. And that's good because otherwise it may run forever really. But sometimes you don't have a choice. So they still exist because not every algorithm can be run faster than this. So there's a difference between time and space complexity, because time complexity is the amount of time that an algorithm runs, like in terms of asymptotic time, right? So like big O of n, for example, right? Like I was getting back to this, right? This would be like time complexity. And space complexity is the amount of memory it takes. So for example, if I have an algorithm here, if I write an algorithm for sorting an array, right? Yeah, if I sort an array, right? And I'm using, if I'm just doing it with the original array and not having, like I'm not putting elements into a new array. Well, let's say I actually want to reverse an array, right? So I have my input array, right? And then I'm reversing it, right? And if I'm using a new array to do that, then it's going to be big O of n for memory, for space complexity, right? Because I have to use big O of n space. I have to provide slots for all n. But if I'm doing it in the original one, it's just big O of 1 because I'm not using any additional space. But with time complexity, right, reversing it, I'm going to have to go through every element, and that's still going to be big O of, right, for time to put it in the new array. Okay, so that makes sense. Okay, so whole question 1. We want to see if this is accurate, right? So best case time complexity for bubble sort is 1 if the input array has only one element. Is that true or false? You guys can pause and answer. Okay, so I guess you've unpaused. So good job. Way to go. Yeah, so let's see. I want to see if the best case complexity for bubble sort is 1 if the input has only one element, right? So this is our bubble sort, right? But as we said before, let's go back to when we said this, so I can show you, right? this is kind of important, is that the best case complexity and worst case complexity are based on like the input, but yeah, like best, average, and worst are independent from input size, right? So in this case, like what I'm trying to say here, yeah, okay, is that that's best, average, and worst case, right? But we want to know about big O, right? We want to know the best case complexity for big O, right? But it's not, right? Because the thing is that we have to go through every element in the array to see if it's sorted, right? We can't just like check one thing. So we have an array here. It's of size n. We don't know how big, right? It's n. We don't know how big it is. It could be any size at all. So even though we're told it's only one element, right? We have to go through all n elements. In this case, n is equal to 1, but we don't know that, right? Like that's not what best and worst case are, right? Like it's still respective, like we still do it respective to the size. So it's false because it's still big O of n. And let's go to the next slide for a little bit of better. So false, yeah. The best, average, and worst cases are independent from input size, as we said, right? It might be in relation to how the input is, right? Like here it's inherent features of the input. So a feature of the input might be a sorted array or might be a irreversibly sorted array, right? That's a feature of the input because it's something about the input, right? Whether it's sorted or not sorted. But here it's a little bit different, right? Because what we're doing is we're just saying it's the size, but it's, remember, big O notation has nothing to do with size. So because we don't know what the size is going to be. Okay, we're told it's one element, but we're still going through n elements where n is just equal to 1. So it's still big O. Okay. Okay. Yeah, or I guess actually it would be big O of n squared. But like because it's sorted, right? We could say that the best case would be O of n, right? So the average case might be O squared for the bubble sort itself. But best case here, because we know it's sorted, because one element by itself is sorted, would be n. Okay. So for asymptotic analysis, we have 4 rules. We have addition, drop constant multipliers, and different input variables. And then we drop the lowest order terms. So what does that mean? Well, let's see. Right, so rule addition. So if we have 2 different loops that operate completely independently, it's kind of like, I don't know, if you have like 2 different things and you're doing them separately. So yeah, let's say I have to go to, how do I say this? Okay, how about I have to do homework, right? And I have to do 2 separate homeworks. And homework 1 is going to take me, or actually I have 2 separate homeworks, right? And my first homework has n problems. My second homework has m problems, right? So n and m. How many problems do I have to do in total, right? Well, or how long is it going to take? Well, I'm going to go through, right? And I'm going to have to do the problems one by one. So I have to do n problems for the first one and m problems for the second. So it's n plus m. And it's a similar thing here, right? You do them separately. So you got, but, okay, yeah. Right, so addition. But one thing that is slightly different, right, is what happens if I have to do them together, right? Like I have to do n homeworks, and I have to do, for each homework, I have to do m problems, right? That's O of n times m. So, for example, if I do, that would be if I have n homeworks, right? And in each of them, I have to do m problems. So that would be like having this for loop, right? It would be like having 4 I to n. And I'm just writing this like pseudocode. And then I would do for j to m, right? And I'm doing them within one another. What this is saying is I'm saying I have n homeworks. Each of them has m problems. In that case, it would be O of n times m. But here, because we're doing them separately, we add. So O of n plus m. This is like having 2 homeworks. One has n, one has m. And this is like having n homeworks, each with m problems. Okay. So we can also drop constant multipliers. Because the thing is that, again, we're considering what happens when n goes to infinity. And at infinity, right, whether it's 5 infinity or 1 infinity, it's all the same, right? It's the same number. things. Like you can create a bijection too. It's the same cardinality. Like infinity, right, is equal to 5 infinity, whatever, right? So here, if we have n, right? Let's say I have 2 homework, each has n problems, right? So it's like that again, right? Now it'd be n plus n, right? But because we assume it, like it's almost like n goes to infinity, right? We drop the constant multipliers. In this case, we have 2 as our constant multiplier. We can drop it because 2n is equal to n, right? At infinity. So we're like assuming it goes to infinity. So we just end up with O(n). Different input variables. So now we consider what happens. We have different input variables, right? So if we have input variable n and input variable L, right? Then again, we have to keep them both, right? Because we don't know which is larger, but they both grow like at the same rate. So here we have this one is O(n), right? And this one's OL. And again, we don't know, right? So you're doing them separately. So you have to keep them both because they're 2 different variables. So O(n) and OL, right? They're different variables, so you add them, and you can't get rid of constant multiplier because there is no constant multiplier, right? Now I dropped the lowest order terms. So yeah, here for this one specifically, this is O(n), right? Because we just loop through all the elements. That takes O(n) time. But for the other one, it's log m, and we know it's log m, right? Because we have this j times equals 2. If we think about it, right, it starts at 1. We go 1, 2, 4 until we get to the number we want. Let's say m, right? And we know it's O log m because that would be like saying how many different times do we have to multiply by 2, or we want to know how many times we have to multiply by 2 to get to m. And that's basically it. We're solving for k. Well, this would be just, what is k? Well, it's log m, right? We know this from like calculus class or algebra class, right? So k is log m. So we know we have log m loops. So in this case, it's O(n) plus log m. Now, remember, if there are 2 different variables, we can't drop m. We have to keep it in there because it's different than n. So we have to keep it in there. But if log m is less than or equal to n, we know that. So like, for example, if instead of m, this said n, then we could just drop the term, right? If this were just log n instead of log m, we could drop this term. And the reason why we can drop it, right, is because it's smaller. But yeah, the growth rate as we go to infinity of n is much bigger than log n. So log n really has no impact. So we just get O(n). But again, if they're different variables, you have to keep both. Okay. Well, question number 2. So you guys can go ahead and try and answer it. Pause and then unpause it when you're done. Okay. So the computational complexity of this algorithm, right? We want to know. And C is a positive integer, right? We know it's a positive integer. Well, any positive integer has to be finite, right? Can't be infinity, right? So yeah, it's a positive integer and it's a constant, right? We say constant, say the word constant. So it doesn't really matter what it is. It could be like 3 or 5 or whatever, right? So as a result, right, what we're saying is like, okay, it's some constant and we keep adding the constant until we get to n. But what that means really is that like, okay, let's say we have C, right? We have to do plus C plus da 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 plus C until we get to n, right? Well, how many C's do we need? Well, we need n over C of them, right? Well, C is a constant, so it's n over some constant, right? But again, we drop constant terms. So we drop this one, like we drop the term, we drop the constant 1 over C, and we're just left with n. So for this one in particular, it's n, right? And inside their O(n) expressions, we're not really worried about this. But for the other one, we have like, right, because like n times the O(n), right? Each time we do O(n). But in the other one, we have I equals n, right? I greater than 0, I minus equals C. And it's the same thing again. where we have to go through how many times we're going through. We're going until I is greater than 0, like until I is like less than or equal to 0. So again, we have to do n over c loops. We drop the term 1 over c, we're left with n, right? So we have our big O is O of n plus n, right? For the whole thing. Well, that's O of 2n. We drop the 2, and we're just left with O(n). Okay. Next question. So the computational complexity of this algorithm. Okay, again, c is constant, so go ahead and pause whenever. Okay, well, in this one, right, we start at 1. So long as we're less than n, we keep multiplying by c. So it's very similar to what we saw before, 1, 2, 4, 8 until we get there, right? What we're really saying, right, is we need to know where c, we need to know k, where c to the k is equal to n. Well, k is log n, right? It's log n, right? And as a result, right, this is going to be log n, this one in particular. However, we still need to figure out what this one is. Well, this one we're doing the same thing because it's just division. So now it's just n over c divided by c divided by c divided by c. So what we're doing n divided by c divided by c divided by c. So we really have the same thing, right? We want to know until this is equal to 0, or we want to keep going, right? How many times do we have to go? Well, we have to go k of them, right? We want to go until this is equal to like 1 or 0. So we have to go k, and again, we're going to end up with like, well, we want to go until like our last term, like one term, right? So we want to keep going until this is equal to n, and again, that's log n. So we have log n again here. So we add them, we get 2 log n, we drop our constant term, and we're left with this. Cool. Okay. So here's a question for you guys. What is the complexity of an algorithm that's counting the number of a's in an array of strings of an indeterminate length? So maybe you're wondering what that means. Let's say we have an array, right? It's an array of strings. We want to know, and we don't know how long any of the strings are. We want to know how long it's going to take to count the number of a's. Go ahead and pause, figure it out. Okay. So, I guess you don't know. Awesome. Good job. Yeah. So to figure it out, we have to know 2 things, right? There are 2 things we want to know. So number 1 is we want to know how many strings are there, right? Because each string we have to do the same thing for. So 1 is how many strings, right? So number strings. And the second thing we want to know, right? Because for each string, we have to count the number of a's. So number of a's in string, right? But it's not just that, right? Because that's the number of a's we want, right? But the thing is that doesn't really matter for our complexities. We have to check every single letter, right, to see how many letters there are. So it's not just the number of a's, it's number of letters, right? Because we have to check every letter and see if it's an a. So it's the number of letters, right? So we have to know the number of strings and the number of letters in the string. Well, that's kind of like how earlier I was talking about I have homework, right? And I have n homeworks. So we can think of the strings as homeworks and the letters in each string as the number of problems in each homework, right? Because it's similar. I have, for each of the strings, I have to check all of its letters. And so if we think of like this as like, well, really what's the most important, right? Because what's the most we'll possibly have to check? What's the longest string, right? Whatever the longest string is, right? That's the most we'll have to check. So we know we have to check less than or equal to the longest string for each of the strings, right? So if we consider the length of the longest string to be m and the number of strings to be n, right? Then for each of the n strings, we'll need to check m letters. So that's big O of n times m, where m is the length of the longest string and n is the number of strings. And so let's look at the solution here. So yeah, time complexity is n times m, where we have number of strings and length of the string, longest string. However, yeah, if we know the strings to be small, if we're told like, oh, the longest string is 10, that's a constant, then we can drop that. So, but because we don't know, it says indeterminate, it's a variable length, right? So m. Yeah, so you can't forget the time complexity of the methods called. So even though it looks like we're just looking at each string, we have to think about what we're doing, which is we have to look through all the letters, right? So that's still m. So yeah, testing equivalence of strings is still an OM operation because we don't know the length of the string. Okay, so now we're gonna move on to a debugging review. Okay. So why do we debug? Well, debugging helps us find errors in code, right? It can cause it to behave unexpectedly. You can walk through, which is good, right? If there's a problem, you can like stop. Advantages of using a proper debugger are ease of use, right? It's easy to use. Easy to use. You can understand how a program works. You can find errors. You don't have to guess and check when you code, and you can stop execution at points in time. And you don't need to like fill it up with print statements. Like that's pretty helpful. So you have to go back and delete the print statement, not fun. So anyway, debugging tools and examples. So basic tools available in debugging are breakpoints, step into, step over, step out, continue. Step into is like when you go into a method. Breakpoints is where the program's going to stop. Yeah, like I said, step into is you want to go into a function. Step over is like there's a line of code and it has a function in it. You don't want to go into the function, so you just step over the line of code. Step out is if you're inside of a function and you want to get out of it, right? Get out, then you step out. And continue is like keep going with the execution. Yeah, runs the program to the next breakpoint execution, so that's continue, and the rest. Okay. Okay, so in this class, we suggest you use VS Code. It's very widely used. I know I've used it many times. Even my internship, we use VS Code. So it's very, very common in the industry and also in classes. So yeah, it's a source code editor. So it's not an IDE. So you have to install a lot of things separately for it. Or not a lot of things, just install it. The compiler for it, C++. But you should be able to just follow any of these until you have a grasp of it, right? Getting a compiler. So generally we use GCC for Windows and Linux, and playing from Mac. And there's a walkthrough here. It's also on the Canvas page. If you have any questions while setting it up and can't figure something out, then you can come to office hours and ask there. That's for coding in Visual Studio. Oh, and you can also just read it out to me. That's also fine too. Coding in Visual Studio. It's Visual Studio Code, right, is what we're using. But this is Visual Studio, which is an IDE. You can also write code there in C++. That's fine too. Yeah, and Visual Studio has some debugging. So this also has a video you can watch. So you can look at these slides as well. But as I said, right, difference between VS Code and Visual Studio is one is a text editor, right, and the other is an IDE. And so VS Code has a lot of language. Well, you can use like basically any language. You can use it for like anything you want to type in. But Visual Studio has like language support built in. And these are some links to helpful debugging tutorials you can look at. So what is Catch 2? We mentioned it earlier, right? It's simple and natural C++ unit testing framework. So it's for unit testing. So why would you use this as opposed to something else? It's nice and easy. It only requires a header. You don't have to like get a bunch of dependencies, download a bunch of stuff, which is nice. And tests auto-register for themselves. You don't have to name everything, which you do with a lot of other things. It's kind of annoying. But with Catch 2, it's good. Assertions are pretty straightforward, and yeah, test-driven development and behavior-driven development. So for the next discussion, please make sure you install this as we're going to go over it, right? Yeah, here's some options. And so writing tests, here's just an example of what it may look like. Yeah, this tells catch to provide a main, so it actually tests your code for you. That's what this catch config main does. You have to include, like we said. And here we're calculating factorial, right? And so it computes it. And then these are just require, it's like saying require, right? Test case tells you, oh, this is where the tests are. And it requires that when you call factorial 1, it's equal to 1, factorial 2 is 2, 0 of 3 is 6. And if these are not true, right, these are assertions, so it's going to fit. Like we said, this tells it to add a main, because every program has to have exactly one main. You include it, and then there's test cases. It's a macro, right? So macros in C++ are things like, yeah, test case. It represents like more code than it is, but it serves a function as just like a word, and then yeah, kind of. Test name, it has to be unique here. So we have a name factorial computed, and then yeah, you run it. And require just the assertions. So this is a tutorial. And then yeah, don't forget, you have an honor log quiz, please do it. And now some extra material we'll get to now. Again, if there's any question about any of the rest of it, like please reach out to me. Yeah. Array versus linked list. So this is something you probably know from programming 2 as well. I think when I took it, at least there's a linked list project. I think it was like the first one. Yeah, so arrays are fixed size, right? And linked lists are dynamic and flexible. You can add more. But with the really big pro of arrays is that you can access any of the elements at any point, right? Because if we think about what an array is, this makes sense. Because an array has a bunch of spots here. You have a pointer to like this element, right? But then you can do pointer arithmetic, right? So I can just move the pointer over 2 spots and just go here. And that's like a 101 operation, however many steps want to move forward. So it's really easy. You can just access any point in memory. The linked list, we only have 1 point in memory, right? And like, we don't know where in memory the rest of it is. Like, it's not contiguous block in memory. Linked lists are just places in memory. You can't move over 2 spots and be sure that you'll get there, because that's not how linked lists are. So you'll have to go like to the next element and the next element and the next element. So I want the 3rd element, I'm gonna have to move over twice, for example. I want the nth element, I have to move over n times. So that's why accessing is O n in a linked list, but O1 in an array. So let's think for a second. 10 people in a room holding hands. Do you want to insert an 11th person into the 5th spot of people? How would you do it? Which is better? Arrays or linked list? Well, we can pause and we can answer. Yeah, so very good. The answer is linked list, right? Linked list would be better. How would we do it? Well, with an array, we would have to, like, we have 10 things, right? We'd have to copy the whole thing into a new array of size 11. Like this one's of size 10. We have to copy the whole thing into something of size 11. And then we'd have to copy all the people one by one, which takes a long time. With a linked list, we would just go to the 5th spot. We have a pointer to the 5th spot. Let's say this is the 5th spot. This one here, actually. Okay, this is the 5th spot. It's 5. Is 4. And this is 6. And this is what we originally have. If we want to insert someone into the 5th spot, what we would do is we'd say, okay, 4, you now no longer point to 5. You point to the new 5, right? We don't have to have them labeled, but like now this one's 6, but you don't have to label them, so it's not a problem, right? 7. It's kind of messy, oh well. And now 5, you now point to 6. And that's it. So it's a lot faster to do it with linked list. Okay, and a lot easier. But for an array, you have to copy everything, and then that's takes long. Okay, I really like this question. When I first heard it phrased to me, it was about like getting out of a desert at a wall. I think this makes a little more sense. But anyway, you guys can read it. I'll be quiet. Pause actually. Okay. So yeah, how would we solve this problem? First of all, any questions? I guess I'll answer any questions you may have. What kind of approaches could we use? Let's just think first. Oh yeah, so for any questions, we want to, let's say we have this door, right? And we have a door here. Like, and we don't know where we are. We're on an infinitely long wall, right? Infinitely long. Somewhere on here, there's a door, right? And we're somewhere on this wall. Let's say we're here, or I don't know, maybe we're over here. We don't know where we are, right? We want to know what's the best way to get to the wall. Well, what is the best? Right? Hopefully that question's cool. What's the best? So I guess the first most natural option, right? Hopefully you've thought about this yourself already, but I'll go over it, right? Maybe the most natural option is to just go one way. And if we do that, that's great. We're guaranteed that if we go in the right direction, we're going to find it the fastest way possible, right? But what are the chances that we went the right way? Just 1 and 2, right? We don't know where the door is. So we maybe went the wrong way. Went the wrong way, we'll never find it. So that's not good. That won't work. So what about the next option? We have to find the way to go both ways, right? So maybe we take 1 step this way, and then we take 2 steps this way. Then we take 3 steps this way, and then 4 steps this way. Well, now we're getting somewhere, right? Because we go 1 this way, and then we go like 1 this way, right? So we have 1 this way, then we go 1 further this way than we went before, and 1 further this way than we went before. Now we're going to get to there, right? But I want you to think for a second. What's the time complexity of that? Assuming that this wall is n, like n, the length of it is n, or for infinitely long, it's n, right? Well, as you may have gathered, right, the distance that we're actually going at first is 1. So we're basically going 1, then we're going 2 the other way, right? And then we're going 3 the other way, and then 4. So we'll get there eventually, right? But until we get to, let's say, n, right? And at n, we're either going to be there or we go n plus 1 the other way, right? But there's a problem here. And the problem is that this, right, sum all the way to n, right? That gives us n squared. So you might think, okay, that's the best we can do. And it's pretty good, right? Because we do get there. Maybe we can do better. And you can also view the question of distance. So how did you find the door? Well, the best solution isn't either of those two, although those are both approaches that we talked about. The solution would be this. You know it's on your left here, right? So you can't walk in one direction randomly. You can walk back and forth at intervals, right? But what if instead of going like arithmetically, right, geometrically, it's like we went 1 and then 2 and then 4 and then 8 in opposite directions, right? That would be much better. And the reason why it's much better is because we're guaranteed that, well, I'll let you do the math. How about that? I was going to work out the math for you, but I want you to think about this. What's time complexity of this? Well, let's see. You can pause and then unpause. Yeah. So what is the solution to time complexity? And if you said ON, you'd be right. Why? Let's think about what it is, right? You go 1, and then you go 2, and then 4, and then 8, and so on, and 16. All the way until you reach n, or maybe you'll have to reach 2n. Either way, right? The worst case is we have to go 2n minus 1, and we see that here, right? Yeah, or I guess, yeah, the most we'd have to walk is 3, right? But what is that? Well, if we think about it, right? If we start adding them, we know that this sum here, right, is at most 2n minus 1. But then we also have 2n plus 3n. Well, that gives us 7n minus 1. We drop the constant factor, we drop the constant term, and we're left with n. So ON. I really like this problem. It's really fun, but okay. Yeah, so this is the source for this. Yeah, so I think that covers everything. Again, don't forget that you have an honor lock quiz due, and I'm gonna upload this. So hopefully you guys all see it. If you have questions about anything at all, feel free to reach out. I know the debugging tools and examples is good. And if you have trouble setting it up, you can reach out. We're using Visual Studio Code for the most part. You can use something else if you want, like you can use Visual Studio, it's okay. But when you're using Stepic, make sure to actually like submit on Step or like test it on Stepic first, because theirs might be slightly different. Okay? C++ is not quite as nice as Java. Things run differently in different places depending on your compiler. But with Java, it's the same everywhere. But like C++, it can be different in different places. So make sure you test it wherever you're going to submit it. Yeah. So you can set it up. You can follow the tutorial online. I think it helps a lot for Windows. Then, all right, so that's about it. Thank you all for watching. Oh, and have an excellent rest of your day, I guess.